Hello, Math 2 Extended. This is Mrs. Bricky, and this video is for Unit 9, Lesson 3. We're going to be talking about the real zeros of a quadratic function today. So your first question might be, what are the real zeros? So the zeros, or the roots of a quadratic function, are the x values for which the function is equal to 0. This is the x values that make the function 0. So for example, if you have the function f of x is equal to x squared minus 4, the zeros of that function are positive and negative 2, because 2 squared minus 4 gives you 0, and because negative 2 squared minus 4 gives you 0. So you can find the zeros, or the roots of a function, by solving the related equation. So you can see that that equation is the same as our function. It's x squared minus 4, and we set it equal to 0. And then we can solve to get the two roots. So if we look at the graph of a function, we can actually see the zeros, or the roots. So here's a graph of that function. F of x is equal to x squared minus 4. You can see that the zeros, or the roots, correspond to the x-intercepts. So this one would be positive 2, and this one would be negative 2. And, for this particular function, x squared minus 4, the y-intercept would be at the y value, negative 4. Quadratic functions with real coefficients have exactly two zeros, or roots. Those two words, they both get used a lot, zeros and roots. So for most purposes, those are interchangeable. So today we're going to focus on quadratic functions that have real roots. In a couple of lessons, in lesson 5, we're going to talk more about quadratic functions with non-real roots. This lesson will focus on real roots. So our first example is going to be finding rational zeros. So if you remember, the real number system has two different types of numbers in it. We have the rational numbers and the irrational numbers. And all of those are real numbers. They're just two different types. Rational numbers are numbers like 1/2 or -3 or -8/7. Irrational numbers are numbers like pi, square root of 2, 9 root 7, maybe negative. Those are irrational numbers. So we're going to do one example where we look at rational zeros, and then we'll do another couple examples where we look at irrational zeros. Okay, so it says find the zeros of the function f of x is equal to x squared plus 5x minus 14. So remember, the way that we can find zeros is to solve the related equation. In this case, 0 equals x squared plus 5x minus 14. Well, this equation happens to be factorable, so we can use factoring as our method of solving it. And if we're thinking about the number 14, you've probably identified 7 and 2 as the two integers that we want to use. And to get the right sign combination for our quadratic, it would be x plus 7 multiplied by x minus 2. So we have two rational zeros. X is equal to -7 and x is equal to positive 2. So this would be the -7 and this would be the 2, and our y value right here would be -14. And in other lessons, we've talked about, how to find that vertex, which we're not going to do today, but you've talked about it in other lessons. Anyway, these are rational zeros because they're part of the rational number system. They're also real zeros because rationals is a subset of the real number system. Okay, so let's think about that same function, f of x, but what happens if we add 4 to it? So I have a new function, g of x is equal to f of x plus an additional 4. So what does adding the constant 4 do to a graph? I hope you remember that adding a constant to a function is going to have the net effect of shifting it up one. So like I'm going to line up g of x with this f of x function, and we're going to shift it. If we add 4, it's like shifting it up 4 units. so here is our new function g of x. So if we wanted to write an equation for g of x, it would be our f equation plus 4 more. So it would be x squared plus 5x minus 10, because I added the 4. The 4 is a constant, so I added it to the negative 14 that the f function originally had. Now, our new function, g of x, is not factorable. There are not factors of 10 that can help us add up to negative 5. So in that case, we're not going to be able to factor it. We're going to have to use a different method of solving. So to find the real zeros of this new function g of x, we're solving this equation, x squared plus 5x minus 10. If it is not factorable, we use the quadratic formula. And let me just write that down. I probably should have just had it ready on my slide, but I did not. Whoops. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So for our equation, our exact zeros are going to be x equals negative 5. Remember the sign change on that b. It's the opposite of b. Plus or minus the square root of b squared minus 4 times a times c. And that is all divided by 2 times a. Okay, so let's see. That square root is the square root of 65. So our exact zeros, so these are irrational zeros, and they are at negative 5 plus or minus the square root of 65, all divided by 2. So those are the exact zeros, but it's hard to envision that. Like, this is negative 5 plus the square root of 65 divided by 2, and this one is negative 5 plus plus, that one's minus 65 root all over 2. The plus one is the one to the right of the axis of symmetry, and the minus part of the quadratic formula is the one to the left in this case. But we can see that the values are around 1.5 and around negative 6.5. So let's go ahead and get the approximate decimals of those as well. Negative 5 minus root 65 divided by 2 gives us about negative 6.53. So that's what this one is. It's approximately negative 6.53. And the reason we say approximate is because it's a rounded value. It is not exactly negative 6.53. It's negative 6.5311288874, etc., etc. But that's its rounded value. And then the other one, negative 5 plus the square root of 65 divided by 2. That one is a decimal value of 1.53. Approximately. So this is an exact number, an exact irrational number, and this is a rounded approximation. Oh, it says round to the nearest thousandth. I'm sorry, those should each have a 1 after them to be to the nearest thousandth. Okay, read your instructions, Miss Bricky. All right, let's try that another time. This time our function is actually given to us not in standard form, but it's given to us in vertex form. So like if we wanted to right now, we could just say that vertex is at negative 310. And the negative 2, again, at the beginning, that is the stretch. So this is going down 2 over 1, down 6 over 1, down 10 over 1 for that pattern. And we don't have a scale on our y-axis, so we can't count that pattern out on the grid, but that's what it's doing. Okay, so again, we can't factor this. It's not even in standard form. So because it's not in standard form, we're not going to factor it, and the quadratic formula isn't useful, but we're finding the zeros of this function. So we're just going to solve this equation. -2 multiplied by x plus 3 squared plus 10 is equal to 0. And because that equation is in that form, we're going to use the square root method to solve it. So I'm going to go ahead and start by subtracting 10 from both sides of my equation. And then I'm going to divide by -2. And when I take that -10 and divide by -2, I get a 5. Now I'm going to use the square root of both sides, apply a square root. That introduces plus and minus symbol. And so now I have x plus 3 is equal to positive and negative root 5. Now root 5 doesn't simplify. You could type that into your calculator to check, but it doesn't simplify. And then we have one last step. If we have x plus 3 is equal to positive and negative root 5, and we subtract 3 from both sides, that gives us our x values. X equals -3 plus or minus the square root of 5. So this one right here is -3 plus root 5, and this one over here is -3 minus root 5. Our y-intercept is, actually don't know off the top of my head. I mean, I could sub in 0 to calculate it, because you can always sub in 0. I'm going to do that since I started talking about it. Y-intercept is -8. And again, I just got the y-intercept by substituting 0 in for x. Okay, let's see. So -3 plus or minus the square root of 5, that's my exact zeros. So let's go ahead and get those approximate zeros, those decimal answers. The first one would be -5.236. And that would be the one on the left. And then the other one is -0.764 if I round it to the nearest thousandth. So those are the approximate zeros. Those are irrational numbers. So just to kind of summarize what we've done, if we have a factorable function, we're going to be able to find the two rational zeros by solving that related equation. If we have a function that's not factorable but is in standard form, we can use the quadratic formula to get the two zeros. Exact would mean that you're leaving it in radical form. Approximate would be that you're finding the decimals and rounding them to some, given number of decimal places. And we can also find the real zeros of a quadratic function that is in vertex form, and we would use a square root method of solving to find the irrational zeros if we have a function in vertex form. So you can probably do most of the homework at this point. I'm going to keep going for the purposes of the video, but you could probably pause and do a little bit of practicing for a minute. All right, so for our second half of this video, we're going to be talking about just connecting some ideas and comparing functions. So here I have 3 functions. The first 2 are in a vertex form, and the last one is in a standard form. So we're going to compare these, find their axis of symmetry, vertex, and their zeros, and then we're going to just classify their zeros. So for our first one, the axis of symmetry, this is a parabola that opens upward, and it has a vertex at -2, -15. So the axis of symmetry of this parabola is x equals -2. And I already found the vertex on my little drawing up there. It's -2, -15. All right, for the zeros or the roots of the function, we are going to be solving this equation. Oh, that's a 15, but it doesn't really look like a 15. So let's see, we would add the 15. I don't usually solve on this side, but you know what? That's what's happening right now. So we're going to root both sides. We have positive and negative root 15. Now that happens to be a radical that does not simplify. So we're just going to leave it in that form. And our final step is that we are going to subtract 2. So we have zeros at -2 plus and minus root 15. So that's an irrational root 15 there. These are irrational zeros. All right, so that was our first one. Our next one, well, it is also in vertex form, opens upward. Its vertex is at -2, -16. Its axis of symmetry is also x equals -2. So this has the same axis of symmetry as our first example. And so if we're finding the zeros of that function, which would correspond to its x-intercepts, we would be solving this equation. So if we add the 16, we can now apply the square root to both sides of our equation. And so the square root of 16 is 4. So this is a positive and a -4 on this side of the equation. And we now have our last step of subtracting 2. -2 plus and minus 4 are our zeros. Now, these are both rational numbers, so we can combine them. -2 plus 4 is 2. -2 minus 4 is -6. So we have 2 rational zeros. Okay. Remember, rational means like that it's able to write as a fraction. Integers count as rational numbers. But if you have a number like root 15 as part of your answer, that's irrational. All right, so this last one is in standard form. So for the axis of symmetry, we're going to have to use our axis of symmetry equation to calculate it. The axis of symmetry is opposite of b divided by 2a. So it's this. And what do you know? It's the same axis of symmetry. So all of these parabolas have the same axis of symmetry. Well, that means that the vertex is occurring at the x value -2, but we need to calculate the y value by subbing -2 in for x. That looks so bad. Oh my gosh, why can't I write? That is a -2. When you're writing on a tablet, 2's are so hard. Okay, let's see. 2 times -2 squared plus 8 times -2 minus 15. Okay, let me calculate that really quick. 2 times -2 squared plus 8 times -2 minus 15. I just got -23 as the y value of the vertex. So this one would be also like the others, centered at an axis of symmetry of -2, but it is way down at -23 for the vertex. Okay, the zeros of this function. Well, I can't use the square root method anymore. You could do some completing the square if you wanted to, but I'm going to go ahead and just use the quadratic formula. So we're solving the equation 0 equals 2x squared plus 8x minus 15. So our x values are -b plus minus the square root of b squared minus 4 times a times, oh geez, that does not look like a parenthesis, times c all over 2a. Okay, so that gives us -8 over 4. Let's see, the square root is square root is 2 root 46. Hope I got that right. Okay, and that's not really very simplifiable, but they are all even, so I can reduce a factor of 2. So our zeros are -4 plus or minus root 46 all over 2. So I've reduced a factor of 2 in each of those locations. Okay, so because that root 46 is there, that's an irrational number. So this function has irrational zeros. Okay, let's see what's next. I hope you noticed that the zeros of the quadratic function, they always come in pairs. I'm going to go back a second. It's like a number that happens to be the axis of symmetry plus or minus some other number. And sometimes that number is a rational number, and sometimes it's an irrational number. And you can see that axis of symmetry, -2, right there. So it's always the axis of symmetry plus a number minus a number. So like if you think about the graph, wherever your axis of symmetry is, your parabola, well, that's not very centered very well. This is this is either the plus or the minus the number, and this is the other side. Now, if it's truly in this form, this would be the plus side and this would be the minus side. But if it has a denominator that's negative, that can be switched. But anyway, these things always come in pairs. When the zeros of a quadratic function are irrational, the two irrational zeros are conjugates of one another. Like if you look at our last, let's look at this one. It was -2 plus root 15 and -2 minus root 15. Those are conjugates. We've talked about conjugates before, mostly in the case of like complex numbers. 2 plus 3i is a conjugate with 2 minus 3i. So these are called complex conjugates, and these are just irrational conjugates. So if you have a quadratic function and you know it has a zero of 3 plus root 7, what is the other zero of the function? Well, we know right away what it is. It's the conjugate of that. It's 3 minus root 7 because they always come in pairs, and we could write them in shorthand like this: 3 plus or minus root 7. Okay. Last thing, we're going to just look at several graphs, several functions, and decide which graph goes with which function. The first set of graphs, we're going to focus on the y-intercept, and then the second set of graphs, we're going to focus on the x-intercept. So I created a graph of 3 functions, but I forgot to label them, and I forgot to include any numbers on the coordinate planes. Silly me. What a silly thing to do. So the 3 functions that I graphed are f, g, and h. F and g are given to us in standard form. H is given to us in vertex form. Thinking about their y-intercepts and which function goes with which, we're going to try to decide which graph goes with which. So let's start with f of x. F of x is given to us in standard form. We're going to think about their y-intercepts, and y-intercept is so easy in standard form. If we think about subbing in a 0, this term is 0, this term is 0, and so our y-intercept is -18. And g of x is also given to us in standard form, so that is also a very easy one to figure out. If we sub in 0, those first 2 terms end up being 0, and you can see that the y-intercept is -5. Be careful if the function is in vertex form. If the function is in vertex form, this number right here is not the y-intercept. It's part of the vertex. My vertex is at, I shouldn't do this in pink. My vertex is at 3, -5. And the vertex and the y-intercept are not the same thing. Like you can see on each of these functions, the vertex is not the y-intercept. So to figure out the y-intercept, we sub in 0 for x. So if I sub in a 0 for x over here, I get 0 minus 3 squared minus 5. Well, this is just a -3 that's been squared. That's 9 minus 5. That's a y-intercept of 4. So now that we have our y-intercepts, we can easily match them. It looks like the only one that has a positive y-intercept is function h. So the green one is h of x. And now we can also see that the blue one has to be function f because it has a y-intercept way down at -18. Oh, that does not look like an 8. It still doesn't look like an 8. Oh, let's label it. That is f of x. And then the pink one with the y-intercept at -5, that one is g of x. So we just compared their y-intercepts to figure out which one was which. All right, let's look at our next example. Oops, I did it again. Another unlabeled, unnumbered graph. The struggle is real. The three functions that I graphed are k of x, m of x, and p of x. You can see the first two are in standard form and p of x is in vertex form. This time our job is to figure out the 6 x-intercepts, which are labeled A, B, C, D, E, and F on the graph. So we're going to find those intercepts and then we can decide which one is which. Okay, let's start with, let's start with P of x because it is the one that is in vertex form. And so we can solve it using a square root method. Let's see. Here we go. X plus 6 squared minus 4 is equal to 0. Well, that means that x plus 6 squared is equal to 4. So if I square root both sides of my equation, I get positive and negative 2 on the right side. And so our x-intercepts are at -6 plus and minus 2. Well, -6 plus 2 is -4, and -6 minus 2 is -8. So we have intercepts at -4 and -8. Now, based on that, I can tell that it's not blue because blue has a positive x-intercept at f. So I know that this is either the green function or the pink function. But right now I don't know which. So I'm just going to write a note to myself that this has to be the green one or the pink one. It can't be the blue one because f is definitely a positive number. Okay, so that was function p of x. Now let's think about function k of x. Well, function k of x, x squared plus 6x plus 2, that is not a factorable function. There are not factors of 2 that add up to 6. So for k of x, we're going to use the quadratic formula. X equals -b plus and minus the square root. Ooh, let's see if I have this fit. B squared minus 4 times a times c. And that's all divided by 2a. And a is 1, so that denominator is just 2. So that's square root. Let's see what I've got. I've got a 6 squared minus 4 times 1 times 2. That is a square root of 28. And if I simplify the square root of 28, it is 2 root 7. And this is all divided by 2. So my x-intercepts are at -3 plus or minus the square root of 7. Now I'm just going to calculate the decimals for a second to figure out. Let's see, that one is -0.35. And the other one is figuring out the decimals to help me place them on the graph. The other one is -5.65. So I can see that I also got 2 negatives again for my x-intercepts for my zeros. So because of that, I know this one is also pink or green. Okay, so it looks like the A value right here, over here, is the lowest of all of the x-intercepts. That's going to have to be this -8. So A is -8. Now, if -8 is on function p of x, then -4 has to be the other green x-intercept. So -4 is going to be this D right here. Okay, so that ended up being, p of x ended up being the green function. And then this -0.35, that's a negative number close to the origin, that's E. I'm going to go ahead and write its decimal If you wanted to, you could write it would be -3 plus root 7, sorry. And then this one has to be the other pink intercept. So if we just wrote down E, this other one would be C, -5.65. That ended up being pink. Okay, so then, well, that means m of x must be the blue one, but we need its values as well. M of x happens to be factorable. If you didn't notice it was factorable, you possibly would just use the quadratic formula, or you could use completing the square, but since it is factorable, I'm going to go ahead and factor it. We're thinking of factors of 7 that add up to 6, so it's 7 and 1. To get a positive 6 as my middle term, here's my combo. So my two x-intercepts are -7 and +1, and that's great because I know f is at a positive number, so I'm glad that I got a positive number pop up. So B would be -7, which makes sense because it's right in between the -8 and the -5.6. And then F would be at 1, 0. Okay, so which of these x-intercepts are rational? Well, the rational ones are A, B, D, and F. And then the irrational ones are C and E. And those irrational ones were -3 plus or minus root 7. Okay, that's it. That's everything. If you have any questions or need any assistance with this lesson or this homework assignment from this lesson, let me know. Thanks a lot.